what is LP little a? How would you describe it to someone that is hearing this sort of complicated term for the first time?
Sure. And the first thing is to just let everybody know lipoprotein little a. It's an inherited disorder, so you have to receive the right genes from mom and dad to have it. But it is the single most genetic determinant of atherosclerotic vascular disease and calcific aortic stenosis. So, two mega pathologies. And it's basically, if you took the whole globe, it's in 1 out of 5 people. In certain populations, like the Africans, it's 1 out of 3. So this is hardly some rare genetic disorder. Everybody has heard about familial hypercholesterolemia, and that has an incidence of about 1 in 200 to 250 people. So you can see, my God, as you walk down the street, 2 out of 10 people will probably have LP little a pathology at work, and the tragedy is they don't know it. It's not being tested by the overwhelming majority of clinicians. So many have not even heard about it. So, with that being said, and this is why it's a topic of interest that you wanted to elaborate further on, because it's a big, big time problem. All right. So you mentioned our previous podcast, we spent a lot of time on the ApoB family of lipoproteins. And just a quick remembrance, ApoB is a structural peptide, a very large protein that has the ability to bind to lipids. And it is the main structural protein that enwraps the lipid moieties that are found in what's called the ApoB family. Previously, they were called the beta lipoproteins, and they include your very low density lipoproteins, your intermediate density, and your low density lipoproteins. Because of its much longer plasma half-life of LDL compared to VLDL and LDL or IDL, about 95% of your ApoB particles are LDLs. So LDLs are actually a heterogeneous family of lipoproteins within a certain density range, and they basically vary by their diameter and a little bit with their core composition. So you have small LDLs, intermediate size, and big LDLs. Now, within the LDL family, an LDL is simply a lipoprotein with one molecule of ApoB on it. So it's LP-ApoB. That is the shorthand signature for an LDL particle. So, but they not only vary by their size, buoyancy, composition, there's a different sort of member of the LDL family, and this is what lipoprotein little a is. So, if I took an LDL particle and somehow attach to it another surface protein which binds to the ApoB, and if I call that other protein apoprotein little a, meaning small case a, not a capital A, for the audience, and there's great confusion on this, lipoprotein capital A refers to an HDL particle. Those are the apoproteins that are structurally found on HDLs. We're talking about little a. So if I took this other peptide and stuck it to ApoB, I have an LDL plus apoprotein little a, voila, that is what a lipoprotein little a particle is. And we'll get into it, but that ApoA is your liver either produces it or it doesn't, depending, did you inherit the genes that make the liver construct that protein?
Yeah, that was what I was kind of interested in next. Where do these lipoprotein little a's come from? Is it that the liver is producing that entire molecule, lipoprotein little a, or is it that the liver is producing the apoprotein A protein, which is going into circulation and then somehow attaching to low density lipoproteins that are already in circulation?
We've come full circle on that, and it's took years to really discover this. This is difficult research. And it was always thought that the liver would produce apoprotein little a and secrete it into plasma, and it would jump on the first LDL particle that cruised by. Then there was a belief that between hepatocytes and the plasma, there's a space called the space of Dis, Disse. And it thought, aha, that's where ApoA jumps on the ApoB moiety of an LDL particle, and then it's released into plasma. Now the consensus, and this is just over the last couple of years, is that apoprotein little a is, of course, made in the liver, but the liver also makes what is called primordial LDL particles. And ApoA joins on the ApoB within the hepatocyte, and then it is secreted as a whole particle. And this is important for so many reasons, because if we understand that step, we might be able to modify the construction step, and that would, of course, affect the production of a undesirous lipoprotein. So it is definitely made in the liver and then secreted. The other interesting thing, in the liver, when apoprotein little a marries this primordial LDL, remember the liver makes a lot of VLDL particles too. But the VLDL is much bigger, has a very different shape, and apoprotein little a will not bind to a VLDL or even an IDL particle. So that's why LP little a is sort of a member of the LDL family, even though it's not really an LDL particle because it's carrying this other passenger, a hitchhiker sort of so that jumps on the particle.
You mentioned at the top there, this is considered an inherited disorder. So just to kind of double click on that, thinking about the synthesis of lipoprotein little a that we're talking about here, and I think you said people of African ancestry tend to have elevated LP little a or at higher risk of elevations.
They're the same
LP
risk,
little a,
but they have much higher concentrations.
much higher concentrations. So is it that their liver, because of some gene mutation, is just producing more of that apoprotein little a?
Correct. So a little bit about how proteins are made in cells, including the liver as a master maker of a lot of proteins. Proteins are constructed in a cellular organelle called the endoplasmic reticulum. And on the endoplasmic reticulum are little subunits called ribosomes, and they gather amino acids and they start sticking them together. And after you get X amount of amino acids bound together, you have a protein or a peptide, whatever, the short protein. But why does the ribosomes do that? Who tells them to make this protein or don't make this protein? And of course, that's our DNA, which is located in the nucleus of the cell. So if you inherit it in the LPA gene, and we have two alleles of it, so you get one from mom and one from dad, so it's called the codominant inheritance. If you get the right type, or maybe I should say the wrong type of ApoA gene that becomes part of your DNA, it gets translated into messenger RNA, which leaves the nucleus, goes over to the endoplasmic reticulum, and it can be read and transcripted into protein synthesis. So if you have the wrong type of LPA gene, you're going to make apoprotein little a. If you don't have those genes, you might not. Adding to the complexity, because we have two LPA genes, one from mom and one from dad, suppose both mom and dad gave you the wrong type of LPA gene, as opposed to neither mom or dad had it. Then you can't have it, and you certainly can't pass it on to your progeny. But if mom and dad both gave you one, you can actually have two types of apoprotein little a. One that will match the one dad's liver made, and one that will match the one that mom's liver made. So when we assay isoforms of ApoA in the laboratory, the majority of people have two types of apo little a floating around. And it's another way of adding to its complexity and understanding its measurement and its laboratory assay. So you could also, of course, if you just got it from mom or dad and not from any other parent, then that's a null LPA allele. So you'll still be making it, but you can blame one parent, not both parents. And listen, nobody's genotyping their parents to know who they got it from. Sometimes, because LP little a is associated with a lot of premature atherosclerotic disease or aortic stenosis, if you can get a really good family history and either your mother or father's telling, oh yeah, my uncle, my brother, my grandfather, they all had a heart attack prematurely, you sort of know which side of the family the LPA had come from or so. So it's just a little clue. In the old days, that was, hey, if you do have a strong family history of premature vascular disease, make sure you test for LP little a. Most of the guidelines have now shifted to, no, it's a mandatory assay once in everybody's life because it is so prevalent. You don't have to test many people to find it. And like any cardiovascular risk factor, the sooner you discover something, there's certainly in the year 2024 and many things we can do about it to ward off some of the misery that it's going to produce. So the genes get translated and then get transcribed at the endoplasmic reticulum, and you are making apoprotein little a. That's the first step. And now you want me to get into how it marries the ApoB, or do you have further questions about the genetic aspect?
Well, let's just pause on the genetic aspect for one moment here, and then we'll move on, because I just want to kind of connect this to something we're going to speak about later, which are the drug trials. And my understanding is that understanding of the physiology, what you've just explained there around overexpression of this gene or increased production of apoprotein little a, has been significant in informing possible medications, interventions that could be used to lower LP little a in this 20 to 25% of the population who have an inherited disorder where they have increased LP little a levels.
That's correct. And this is true with so many diseases, as we're far better understanding what proteins our genes made, and if they're bad proteins, if we can interrupt through screwing up some of the genetic mechanisms, you might not produce a adversarial protein. So that's exactly where we are right now. They're still in testing; they're not available yet. But you have drugs that stop the translation of the DNA into RNA, the antinucleotide oligopeptides that interrupt translation. And then you also have the small interfering RNA that interfere with the RNA development. And if you screw up the RNA development, there'll be no transcription of the RNA out in the endoplasmic reticulum. So you have two genetic ways that you can stop, hinder, slow, arrest the production of apoprotein little a. And to make this how important this is, look, if you have something floating in your plasma, you can alter it either by stopping its production or enhancing its clearance. We have almost no information even on how LP little a is cleared from plasma, and therefore we have no therapeutics that will increase the clearance to a serious degree of LP little a from plasma. So if we are going to reduce the dangerous LP little a concentrations, it's going to be by inhibiting production. Now, there are also one last thing, that's the genetic approach to it, but there are other intracellular hepatic approaches that you can prevent the marriage of apo little a. Even though it's being made, if you can prevent it from adhering to a primordial LDL particle, then you cannot make LP little a. So that is a very viable approach also. We actually have a drug on the market now that does that to some degree, and one is in development.
So by primordial LDL particle, again, I'm just throwing this back to you to make sure I'm understanding this correctly, but you're talking about an LDL particle that's produced in the liver and is kind of secreted into circulation from the liver versus a LDL that is produced from VLDL and IDL dumping off triglycerides.
Correct. That would be called the lipolysis of those bigger triglyceride-rich lipoproteins. When you shrink them enough, they enter the buoyancy of an LDL. LP little a particles, that is not the LDL they join. Even if you don't have LP little a, upwards of 40% of a person's circulating LDLs are primarily produced in the liver. They are not products of VLDL lipolysis or catabolism. So in the liver, I told you, all right, the ribosomes might be making apoprotein little a if you inherited the gene, but everybody's liver is synthesizing apolipoprotein B, and apoprotein B, like apolipoproteins, binds to hepatic pools of triglyceride, cholesterol ester, and phospholipids. And before you know it, I call it a primordial. It's like a little baby LDL, but it matures as it wraps and gathers more lipids. Then you have a LDL of a density that's going to be floating in your plasma. But before that LDL leaves the liver, apo little a jumps on it, and then the liver just secretes. So the liver is secreting both regular LDL particles, and it's also secreting LP little a particles. And of course, the majority of your LDLs, 60% of them that are in plasma, do come from what you said, the lipolysis of VLDL and IDL particles. So you actually could, if you got the wrong genes, you got two types of LDL particles floating around your plasma, LP little a plus there's what should we call LDLs that don't have apo little a on it? A non-apo little a carrying LDL, but that's a mouthful. So as we get into this, I'm just going to, if you hear me say normal LDL, that means an LDL that doesn't have apoprotein little a attached to it. But never forget, LP little a is an ApoB particle. I told you an LDL is LP-ApoB, and LP little a is LP-ApoB-Apo little a. You're just listing the protein contents of a various particle.
I'm interested in what the potential functional role is for apoprotein little a. Why would 20 to 25% of the population be producing more of this? And if we kind of go back to our original discussion, just to bring everyone back up to speed, and you've just gone over some of this physiology, my understanding is that if we think about kind of the lipid transport system, ApoB containing lipoproteins are essentially just like buses. The proteins, the ApoB, the protein is like a bus that allows lipids, which wouldn't dissolve in water or in circulation, to be carried through circulation so that we can get energy, triglycerides, from the liver and from our food to cells to make use of.
Correct. And to finish that, when those ApoB particles delivering triglycerides, kilos from the intestine, VLDLs from the liver, what's left? Cholesterol. That is immediately brought back to the liver. So ApoB particles deliver triglycerides, energy, also phospholipids, but to the periphery, but they bring cholesterol to the liver. The ApoB particles, with unusual exception, do not deliver cholesterol to tissues. A crucial concept, because too many people panic when they see very low ApoB cholesterol, that would be non-HDL cholesterol or LDL cholesterol. They think bad things are going to happen. No. Tissues make their own cholesterol. Tissues do not need a delivery of cholesterol. But muscle tissues that require a lot of energy do need a delivery of triglycerides. Phospholipids that break off are used by HDLs in plasma as they mature, but cholesterol back to the liver. Now, I don't know, your question is going to be, what does LP little a do? Is that a viable part of the lipid transportation system, or is it an aberrant part? Why the hell did it ever appear? If we have genes that make it, why? So is that where you want me to go?
Yeah, that's exactly where I wanted you to go. And let me just recap. I have a quote here from, I think it was Peter Toth. You sent me this paper, and this underscores what you just said. And still to this day, I see people saying, you don't want low cholesterol because it's important for your cells to produce hormones and for cell membrane fluidity, all the things that you have thoroughly walked us through and debunked. But I just want to read this quote out again so this really lands for people. All somatic cells, including astrocytes and oligodendrocytes in the brain, make cholesterol through the same pathway that the liver utilizes and can obtain some from high-density lipoprotein. Even when low-density lipoprotein cholesterol is extremely low, there is no impairment of cellular cholesterol production and utilization within the brain because the brain produces its own pool of cholesterol, as do all cells in the body. No tissues depend on cholesterol transfer from LDL cholesterol.
Yes, and quick proof of that is the people who have genetic issues where they just don't make ApoB particles, hypo-beta lipoproteinemia. They go through life with incredibly low LDL cholesterols under 40. And it's nice because they don't get atherosclerosis, but they don't have any cholesterol deficiency issues in their brain, their adrenocortical tissues. So all the cells are happily making all the cholesterol they need. But a little quick aside, because I'm not exactly sure you said it, HDLs can deliver some cholesterol to your gonads and to your adrenal gland, but not to the brain. ApoA1 can leave an HDL and cross the blood-brain barrier and be used to help make a brain lipoprotein, but it doesn't drag cholesterol with it through the blood-brain barrier. So ApoA1 leaving plasma and going into the brain, we believe in the future that's going to be a viable way to treat dementia because they have screwed up brain lipoproteins due to the ApoE4. And ApoA1 might go in and make the brain start constructing normal HDL particles, which can help get rid of the amyloid and the tau. It's a whole nother topic. Get me back, and we'd love to go through that.
Yeah. So back to LP little a and its functional role. I've heard some speculation that maybe this kind of subtype, specialized form of LDL, low density lipoprotein, that has this apoprotein little a on it is important for wound healing. So perhaps it's a genetic variation that in years gone by, it was important for short-term survival with long-term survival trade-offs. Is there any accuracy to that speculation?
There's a lot of speculation by people a lot smarter than me who investigate ancestral genes as to why we have them. Did they disappear? Did they not? Or why did some linger? And that is the prevalent theory. One of the perhaps functions of apoprotein little a is it's a procoagulant, and it can promote wound healing, as you said. So you can imagine 15,000 years ago when we're climbing trees or out in the jungle where trauma is so prevalent, if you had something that could rush to a traumatic tissue injury and stop hemorrhage, number one, and then promote healing, boy, you'd want to have that gene. And the people who selected that gene would have a survival advantage, of course. But as humans evolved, all of a sudden, trauma is still important, but far less important than it was back then. And now all of a sudden you're carrying a procoagulant lipoprotein, which of course could lead to strokes and heart attacks and tissue coagulation where you wouldn't want it. So is that what it's from? Interesting, the apoprotein little a, the gene that causes its manufacture, is sort of a derivative of plasminogen, which is one of we have a whole family of proteins that regulate coagulation. Plasminogen is a precursor to plasmin, which is involved in the fibrinolytic process. It stops fibrinolysis, or it promotes fibrinolysis, which is part of wound healing. As you get a clot in any tissue, you don't want that clot to stay there forever. Once the bleeding is stopped, the body then has to go in and remove that clot, and plasmin is what does that. And it is known that one of the, maybe in the past, good functions, but a modern function of LP little a would be to inhibit fibrinolysis, which would promote clotting. So, and where atherosclerosis is concerned, you don't want procoagulant type peptides floating around because that technically could worsen it. And that's thought to be perhaps, if LP little a is currently very bad for atherosclerotic production, is part of it because of its thrombotic properties or so. That is starting to take a little back seat, but for the longest while. So that's likely the evolution of the gene and why, back in the day where you had plasminogen making an accessory plasminogen gene, which is like the gene is much smaller for apoprotein little a than it is for um, plasminogen. So, but it still probably served the procoagulant function in the old days, as it does now. Desirable years and years ago, not desirable now. Look, as we are getting smarter and smarter, more and more studies come out, the list of what LP little a does went from one or two things to about 6 or 7 things now. So it's a very complex protein that seems to have a lot of effects involved even with the innate immune system now that is almost certainly why it does or what it doesn't do to various tissues, including plaque in the arterial wall. So,
the procoagulant properties that you're talking about now remind me, and I want to put a pin in this. I want to come back to this, but they get me thinking about fish oil and aspirin, which a lot of people are talking about with regards to intervening on LP little a in the absence of lots of clinical evidence. So let's come back to that. But just to kind of summarize why this conversation is really important and why we're going to dig into how LP little a is affecting physiology and what its various properties are. What do we understand about the risk that elevated LP little a poses? So if you are one of the 20 or 25% of humans with elevations in LP little a, how is that affecting their risk of disease and mortality?
yeah. And it's almost two separate discussions because one is what it does to the arterial wall and atherosclerotic plaque, and the other is what does it do when it invades your aortic valve and interacts with the interstitial tissue in the aortic valve. They're slightly different mechanisms as to how it screws the aortic valve and how it does plaque. With respect to the atherosclerotic plaque, which is the major thing most people think about it, although doctors should certainly always have aortic stenosis high on their list of things to evaluate in a patient with high LP little a. For years, it was thought, oh, it's just a procoagulant protein. It's antifibrinolytic, and coagulation is so important to worsening plaque. You don't want clots to persist in plaque. A plaque would grow and expand and then get into the lumen. So that's why LP little a is so bad. And then the thought came by that, geez, if it's such a procoagulant, why is there no venous thrombosis with LP little a? If it's really that much of a procoagulant, there should be at least some increased incidence of venous thrombosis. And for years, we were all taught that there was, but it turns out there really is not, with an unusual exception. And the Mendelian studies that looked at LP little a really saw no venous thrombotic pathology in the patients who've had high, but of course, there's a lot of atherothrombotic complications and the aortic stenosis. But it was all dismissed that there is one tiny group of people with LP little a who do get venous thrombosis. And it's those that have LP little a at the 99.9 percentile. So they have such astronomical levels of LP little a that I guess at a certain concentration threshold, it might affect venous coagulation also. But for the vast majority of the persons with high LP little a, they usually don't have values of that extreme. So no venous thrombosis.
Why is that an important observation, Tom? Because I think similar could be said about ApoB containing lipoproteins kind of invading the wall of a blood vessel. We see that ordinarily in major arteries, coronary arteries, for example, not necessarily in veins. It doesn't mean that ApoB containing lipoproteins are not atherogenic or potentially atherogenic. My understanding was that we're talking about two different environments, so that how they affect the artery may be different due to the local environment.
Sure, and remember, ApoB particles invade the artery wall. It's pretty much in numbers. Across above a certain threshold, the ApoB particles still start to go in. That's not true with LP little a particles. They can gain entry into the artery wall even when they're subtly elevated. Of course, if there are more of them, more will go in, but it's not a concentration gradient driven entry into the artery wall like an LDL particle is. And there are a variety of receptors, either in the endothelial cells or even in macrophages that are circulating plasma, that can bind to the LP little a and carry on the endothelial surface. They'll just pull it in and it'll get into the arterial intima. Whereas a monocyte or a white blood cell carrying apo little a through chemotactic proteins can just be also pulled into arterial walls. So it gets in a different fashion. Once it's in, though, it's because of the distinct properties of LP little a. Once it's in the artery wall, it is very pro-inflammatory, and we're going to, in a little bit, certainly get into the reason as why it's so pro-inflammatory. But it is pulled in by toll receptors into arterial wall, monocytes, macrophages, and that sets off a whole synthesis of all the cytokines, chemokines, all the inflammatory junk that can come out of the white blood cells that are all part of the atherogenic process within the artery wall. We all know the ApoB particles go in and start it, but it's a very pro-inflammatory state that soon results in there, and LP little a contributes to that big time. It also can make the platelets more reactive, so that would, even in the arterial wall, again, you're going to have a more thrombotic cascade into plaque development. Interestingly, it also, if you think of the arterial wall, you have the endothelium, then you have this intimal layer of sort of connective tissue, and then on the towards the outer surface of the artery are your muscle cells, smooth muscle cells, which is what makes the arteries contract and everything. But part of plaque is when we start getting these foam cells, cholesterol-laden foam cells, an inflammatory mess, and they start sticking together, and you have this mass of lipids. Part of the defense mechanism is for smooth muscle cells to migrate from the external surface of the artery more towards the endothelial surface and start surrounding the plaque. And people have heard of the cap of plaques, and that is smooth muscle cells. But these smooth muscle cells also, when they get around the plaque, they start secreting connective tissue, which again, they're building a wall around the plaque, which is good because that will stabilize the plaque, make it less likely to rupture. LP little a makes those smooth muscle cells behave aberrantly. So yes, they're recruited there, but they're not creating this protective matrix around the plaque. So it's one way of creating to plaque instability. So you don't want LP little a particles in your artery wall. So I really should then jump to what is it about an LP little a, apart from its thrombotic properties that is inducing white blood cells to create this inflammatory mess, recruit smooth muscle cells, making platelets stick together. And it's something that the apoprotein little a carries into the artery wall. So, and this might get back to another function of LP little a. Maybe now, I don't know if in yesteryear, if it performed this function, but apoprotein little a is a peptide that consists of units that adhere together. And when you stick all of these units together, you have apoprotein little a. And these are peptide units. Each one has about 90 amino acids. And because there are some cysteine groups in there, cysteine has a sulfur molecule. So if I take a length of a protein and I scatter, say, 3 of these cysteine molecules with sulfur atoms sticking up, sulfur loves to bind to each other. So all of a sudden that linear protein starts to curl up. because the sulfur bonds start binding to each other. So all of a sudden, that straight protein becomes a series of looped proteins, looped peptides. And each loop is called a kringle. And whoever named them said, you know what, this looks like the pastry I had for breakfast over there in Denmark or Sweden or somewhere in Europe. Kringles are what pastries are called. So somebody said, these loops of amino acids look like kringles. So the name has stuck. So apoprotein little a consists of X number of kringles. All right. So remember, it's derived genetically from the plasminogen. Plasminogen has 5 kringle components, but apoprotein little a is sort of a truncated plasminogen, so there are only 2 kringle units. Plasminogen would have kringles 1, 2, 3, 4, and 5, either described with a Roman numeral or an Arabic numeral, or whatever you want to write it as. Apoprotein little a has 2 kringles, 4 and 5. There are no kringles 1, 2, and 3 that those genes got lost as the gene for LP little or apoprotein little a was evolving. But it gets more complicated. Kringle 5 is exactly like the kringle 5 in plasminogen. But kringle 4, and this is where things get ugly, but you're just going to have to understand this. You want to know why it's bad and how we have such trouble measuring this in the plasma. So kringle 4, we now know, consists of 10 subunits. Kringle 5, there's no subunits. There's just kringle 5. So kringle 4 has 10 subunits. So you might say K, Roman number 4, but then there's a subscript 1-10. So are you going to talk about kringle 4, subunit 1, subunit 2, blah, 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 subunit 9, 10, whatever. And kringle subunit 1, 3, 4, 5, 6, 7, 8, and 9, and 10 are all identical. But kringle 4, subunit 2, and this is where the genes cause the havoc, you can have 1 copy of kringle 4 subtype 2, or you could have 50 copies of it. Now think of it. Remember, although it's a loop protein now, you can imagine if kringle 4 section 2 had 50 boy, that'd be a lot bigger kringle than if you only had 1 kringle 4 2 subunit. So obviously that's going to affect the molecular weight. So if you had 50 kringle 4 type 2 subunits, you'd have a very large peptide with a very high molecular weight. But if you only had a couple of repeats, you would have a low molecular weight apoprotein little a. It's called small or short. So there's a lot of adjectives you're going to hear thrown around with lipoprotein little a. Are you talking about the small LP little a, large, high molecular weight, low molecular weight? Understand that small is identical with low molecular weight, large is identical with high molecular weight. The other thing that adds confusion is because for years we've been told LDL particles come in big and small sizes. When we say small LP little a, we are not referring to the diameter of the LDL moiety of lipoprotein little a. We are talking about the molecular weight of the apo little a peptide. So it gets very confusing. Now, even remember, LP little a has an LDL moiety. That's what's at its center. And that LDL can vary in diameter. So LP little a particles, their LDLs can be small, intermediate, and large. But that has nothing to do with the size, the molecular weight of the peptide apoprotein little a. So you can see people throw around these terms small and large in a very confusing manner. So you should learn these terms so you know what people are talking about when you read about LP little a. You with me so far?
I have a lot of questions. I think I'm with you most of the way. I'm sure I don't appreciate the deepness of the physiology there, but my question here is: what I'm hearing is that a kringle 4 subunit 2 polymorphism, that is what is associated with most risk when we're talking about LP little a. My question is that what drives the elevation, or is it possible to have two people who have elevated LP little a, but the kind of structure or the shape type of that LP little a is vastly different due to this kringle that you're talking about?
Correct. And this is again why this can be so, it almost takes you a month of reading to put these. I got to send you some graphics where it'll be very easy to understand more than me describing it. But you're right. And remember what I said before, too. You can get one LPA gene from mom and one LPA gene from dad. And the one from dad may produce more Kringle 4 subtype 2 repeats than the one from mom. So you're going to have actually two types of apoprotein little a floating around, a low molecular weight and a high molecular weight. So it gets confusing. But now here's the other thing where this is so crucial. And you imagine that you're one of the little workers in the endoplasmic reticulum ribosomes that has to make this protein. And this is almost like a kindergarten question. What do you think it's easier for the ribosome to make? A very small apoprotein little a or a gigantically long apoprotein little a, the high molecular weight? Common sense tells you it only would take a few amino acids to make a couple of repeats, a low molecular weight, and I would have to round up a hell of a lot of amino acids to make 40 copies of Kringle 4 subtype 2. So the production rate of apoprotein little a varies tremendously whether your genes are telling it to make the low molecular weight or the high molecular weight. So step 2. If it's so easy and so quick to make the small, low molecular weight isoforms of apoprotein little a, and once they're made, they're shoved out and they go and bind to an LDL particle, and then you've created an LP little a. If it's going to take a lot longer to manufacture a large molecular weight apoprotein little a, you're going to produce less of them. So the people who have the low molecular weight, the small ApoA, have astronomically higher LP little a concentrations, and it's totally due to they're so easy to produce, and you can produce them in quantity. If you're making the big apoprotein little a and you got this gigantic peptide, it's also subject way more to proteasomal degradation, even in the endoplasmic reticulum, than is the small one. So if you're producing big apoprotein little a, it takes a long while, and a lot of them are deconstructed before they even jump on an LDL particle. So even though you're making big apoprotein little a, you will be producing far less LP little a particles. In the old days, we used to, before we knew this, we'd say, oh my God, if you have the small isoform of LP little a, you're the one who's going to get the heart attack. We now know, sure, that's because your LP little a particle concentration is through the roof if you have the small isoform. If you make the big isoform, your LP little a concentration in plasma will be much lower and your risk will be much lower. But remember, maybe you got one from mom, one from dad. So your LP little a concentration, X amount is going to be the small isoform, X amount is going to be the big isoform, but it's really the small one that is driving the total LP little a concentration. Boy, I hope I made that clear. You can better, probably, I hope, put my words together and re-explain that, Simon.
No, I think it's clear. I mean, one of the takeaway points for me there, and this sounds like a similar conversation to what we've had with ApoB and cholesterol, in that it's the particle number, the number of ApoB containing lipoproteins, that drives the risk, and that is why there's been this push and move towards measuring ApoB, because there's one ApoB per ApoB containing lipoprotein, so you can get a clear look at total particle count. What I'm hearing from you here is this is a similar scenario with LP little a, in that particle number is more meaningful than mass, which from my reading seems to be contested or debated. I've seen, World Health Organization recommending ordering blood tests that look at milligrams per deciliter, which is more of a mass kind of assay versus other labs that look at nanomoles per liter, which is, I guess more of a particle count. With your understanding of the different sized LP little a's and what's driving risk, what do you think we should be measuring? Is it just measuring LP little a particles?
Yeah, your analogy to ApoB is spot on. What it matters is the particle number. How many LP little a particles are in your plasma? It doesn't matter the isoform per se, except there's just a great correlation between the small isoform and the particle count. So, but even if you have small LDLs, your ApoB count is higher because those particles are not clear. But it's just like ApoB, it's particle number. And this is why genetic testing, you do not have to know the isoforms of, doctors still ask me, hey, what lab will give me whether I have small or big isoforms? No lab out of research, and you don't need to know that. All you need to know at the bedside when you're evaluating patients is the absolute concentration particle number. We've got to come back to this, but you did bring up the assays, and this is, again, big confusion out there in the real world. You might order an LP little a concentration from whatever lab a practice uses, and you might get it reported to you in what is called mass, which is milligrams per deciliter, but you might also get it reported in molar concentration. Remember, mass is your weighing whatever the hell you're measuring, whereas moles, you're counting number of atoms, number of particles. If you want to look at a molar concentration of cars, it's how many cars are driving down an X amount of the highway or so. So you're counting things with molar. Then this is why they want you to get a lab that has assays that report out to molar concentrations, because you have a much more accurate assessment of the number of particles. Now, if your lab is using the type of assay that will not report out in molar concentrations, and there are issues with them, but they're doing it the old way, the mass, LP little a mass, what they do is they take a blood specimen and they take the A particles, they isolate them because they have an antibody that binds to apoprotein little a. It's a nonspecific antibody, but all of a sudden you've rounded up the LP little a particles, and then they weigh the whole damn particle. So what you're assaying is basically the molecular weight of apoprotein little a, the molecular weight of apoprotein little b, the molecular weight of any other proteins that happen to be on there, and there are others, but also the molecular weight of every phospholipid that's on the particle, the molecular weight of every cholesterol ester molecule, which there are thousands, the molecular weight of every triglyceride molecule, and the molecular weight of any other lipid or sugar that's on the LDL particle. So you're weighing that. Now, the lab has measured maybe your ApoB concentration. So, and that's the same thing. They can do an individual assay because ApoB is a distinct protein that you can develop an antibody to, whereas apoprotein little a is not a distinct protein that you got an antibody that can pick up every distinct isoform because of the variant number of copies on there. And the other cool thing is if I measure ApoB, and the labs do report that in milligrams per deciliter, but it's one peptide. We know the molecular weight of apoprotein little a. So we can easily convert apoprotein A milligrams per deciliter concentrations to nanomolar concentrations. It's a simple calculation. Just like you can take cholesterol in milligrams per deciliter, because cholesterol has one molecular weight, you can easily convert it to moles of cholesterol. You can't convert milligrams per deciliter of apoprotein little a to molar concentrations because of the incredible variability of the apoprotein little a molecular weight. There's a cheating way of doing it if you want to say, well, the average molecular weight of apoprotein little a is this. A conversion factor of anywhere between 2 and 2.8. If you multiply the milligrams per deciliter, it'll put you in the ballpark of where the molar concentration is. All the guidelines would be smacking me saying, don't tell them that. We don't want people doing the conversion because it's kind of inaccurate. And I'll close with this. Really, the people we worry about are those going to be very high mass or very high particle concentrations. If what your lab is using a mass assay and it's in the very high range, you certainly will have a high molar concentration also. And likewise, if you have a very high molar concentration, if you repeat it measuring mass, it's also going to be very high. It's not like you could have low mass measurements and have very high particle measurements. They do correlate somewhat. But as we're going to get into therapies and you're really going to have to know how many particles you're reducing, we really have to graduate, just like we have with ApoB and LDL particle counts using NMR, to particle numbers rather than guessing by LDL cholesterol and in a similar fashion. So, the last thing is for laboratories to have assays that can accurately measure molar concentrations, there is still no standardized assay that can do that. Labs use different assays, so my LP little a in one lab might not exactly jive with my LP little a in another lab. The WHO has put out an assay that has 5 types of ApoA in the control, so the labs are supposed to match the antibodies they're using to measure LP little a to the 5 distinct calibrators. And some labs do that and some don't. But even if you're doing 5, there are so many different more variables in the types of isoforms you could have with ApoA. You will never have an immunoassay that's super accurate with LP particle counts. They're working on mass spectroscopy ways of doing it, but that's far in the future.
Is that why you hear stories of individuals who say, hey, I retested my LP and it was 20% lower or 10% higher? Is that because if what we're talking about here is something that is almost entirely driven by genetics, you would expect your exposure level to be pretty consistent, the particle count to be pretty consistent in circulation if it's not being influenced by environment. So if we're seeing, and some reports I've read suggest a kind of 20 to 25% variation within individuals on repeat testing, is that not something that is explained by biology, but is explained by the way that we're testing it?
Yeah. Now, technically, you should have an exact level of LP that never changes. And we know from pediatric studies, by about the age of 5, people have developed their adult LP concentrations. And technically, that should be the same because you didn't get any different genes as you grow older and older. But as we're learning now, there can be some variability. Inflammatory states, your liver will produce more apoprotein a in what's called the acute phase reactant, where the liver starts producing a lot of proteins. There are certain hormonal things that can vary a little bit, including estrogen, so it may vary a little, but it doesn't vary very much. When a woman goes into menopause, the loss of estrogen, LP can go up a little bit. You hear about diets and nutrition. If you read the textbooks, should have no effect on it, but there are emerging things that people on certain diets maybe can lower a little, but you're not going to reduce it like the drugs that are coming can reduce it. So you get this small variability that you're talking about. So the most common thing, I get emails all the time, oh my God, my LP here was this, and now it's like 5 times higher. Rule number 1, they're comparing milligrams per deciliter with nanomoles. They're not looking at the units of what the hell the lab reported it in. But other than that, some of the issues I talked about can do that. And if there is a food variability, it might be true in some people who have certain genotypes and not with others. But it's not going to be drastic. I joke, I got an email 2 days ago, like where somebody went up like 150 points. I said, did they get a liver transplant? If you have high LP little a and you get transplanted with a liver that doesn't have the LP little a response element in the gene, you won't make LP little a. Or did that person suddenly go into kidney failure, which can shoot up LP little a through the roof? So now that's a rare, though, liver transplants is that's a crazy question, but renal failure is a common doing. But it shouldn't vary that much. What you said is probably true. The assay in the lab, they're just not that well standardized, so it can vary a tiny bit time to time. And this is why you got to be careful, because every time somebody eats some bizarre food and their LP little a drops by 20 milligrams per deciliter or 50 nanomoles per liter, they think they've discovered a cure. They have not. Those type of subtle drops, if you have a very high LP little a mass or particle number and you drop it, you're still in the high risk range. You haven't done anything. You have to dramatically reduce LP little a to reduce at least the pathologies we're talking about. So yeah, it can vary a little bit, but you're never going to go from perfect to normal without a drug.
You guys know this already. At the center of good health lies a healthy microbiome. When you feed your microbes, they reward you with drug-like compounds that improve blood sugar control, lower inflammation, act as precursors to important neurotransmitters in the brain, and plenty more. Step 1 in achieving this is a prebiotic-rich, plant-based dietary pattern. If you want to go a step further, you can add a prebiotic supplement to your diet, providing your microbes with extra fuel to grow stronger. I personally start my day with 38 Terra's Daily Microbiome Nutrition, or DMN, which I had the privilege of formulating alongside gastroenterologist Dr. Will Bolsowitz. This is hands down a best-in-market, complete prebiotic with clinically proven ingredients such as actazine and solnol that have been shown to improve gut barrier function and normalize bowel movements. It's like doing the reps in the gym, but for your gut. Get 10% off your DMN at 38terra.com using the code THEPROOF. That's 38TERA.com and use the coupon code THEPROOF for 10% off. When you say high risk, because I realize we haven't really defined this yet, but let's say someone goes out and they do measure nanomoles per liter, so they get a kind of particle count. And I've looked at risk thresholds from different consensus guidelines. It seems to be a little different across the world, with some guidelines suggesting anything over 100 nanomoles per liter is kind of, you're in high risk territory. Some saying over 125 nanomoles per liter. So I'll get you to comment on what you think is high risk, but then also, Tom, how is that affecting? Because here we're talking about atherosclerosis. I want to come back to aortic valve complications, which, because you kind of said at the beginning, we need to treat these two separately. But if we think about what we would say is an elevated LP little a, whatever that figure is, how much is that increasing someone's risk of atherosclerosis?
Well, you're going to be speaking in generalities. Just like with high ApoB, there are some people who got scary levels and they don't seem to manifest atherosclerosis. They're a minority. But as scary as LP little a is, which I started off the first statement, it's the most inheritable cause of atherosclerosis, is there are people with high LP little a who do not get atherosclerosis or aortic stenosis. If you're a clinician and you measure it and it's very high, you should assume that person is going to be at very high risk. But one day, perhaps, and I think it will come with accessory tests that we can evaluate, my God, you're the one person with very high LP little a we don't have to worry about. But for now, let's use what is considered you're in the danger zone or you're not with LP little a. And there would be two sets of metrics, depending whether you're looking at milligrams per deciliter, LP little a mass, or molar concentrations, LP little a particle number. So with the mass, normal is considered under 30 milligrams per deciliter, but the guidelines will tell you you're not going to be in big trouble until it starts hitting 50 milligrams per deciliter. And maybe even when it gets to 70, that's the really high risk with LP. But the 30 milligrams per deciliter is the 70th percentile of the human race. So that's a pretty high threshold. And, when you're starting to talk 50 and 70, you're into the 90th percentiles of what they should. They should be scary levels. So with respect to particle counts, normal would be an LP little a particle number under 50 nanomoles per liter. And the guidelines will, and they differ a little bit. As you said, you might see 100 nanomoles per liter, 125 nanomoles per liter as, oh my God, you're now in the high risk territory because you're starting to approach the 80th and 90th percentiles of LP little a in the population. Now, there are some people who go up to 200, 300. I mean, there are some oddballs out there with 500 or 600 nanomoles per liter. But I don't know, are they at that much more risk than the people who have 250 nanomoles per liter? Before I said, well, maybe the super extreme ones would have a little worry for venous thrombosis too, but I think their atherosclerotic risk is very high. Like everything else, there have been suggestions by some of the experts. No guideline says it per se, but if we had two people with the exact same it's in the high risk territory. Is there a way of saying who would even be higher risk? You basically start looking at other risk factors. So if you also have an extremely high LDL cholesterol, non-HDL cholesterol, ApoB beyond your LP little a, if you have hypertension, if you're a smoker, if you have coagulation disorders, diabetes, they would make whatever a given LP little a number is worse. But that's almost true with ApoB too. So if you had an isolated ApoB and I subsequently found out, oh my God, you're hypertensive, diabetic, strong family history, you'd worry about that ApoB a little bit more. So it can be influenced by what else you might be dealing with a person. But those are the numbers that at least would scale you into the lower, intermediate, or high risk zone with LP little a.
Tom, if someone's listening and thinking, okay, I haven't measured LP little a, and I've heard Tom say that LP little a is one of these ApoB containing lipoproteins. It falls into that family. And they have measured ApoB and it is optimal. So let's say it's physiologic. It's 30 to 50 milligrams per deciliter or even lower. And let's just presume in this example that we're talking about someone with amazing genes or someone that's taking lipid-lowering drugs to get down to that level. And they're thinking, well, I've kind of measured ApoB and LP little a falls underneath that umbrella. Is there a need for me to even go out and measure LP little a?
The answer would be yes, twofold. One, you can do cascade testing in your first degree relatives, your children, your brothers and sisters, aunts and uncles. Say, hey, you go get LP little a checked. So it is an abnormal genetic disorder. So you can advise relatives to get it checked if you have discovered it. But if you have an ApoB of 30 or less, here's where I think you still could be at risk. And this comes out of the two recent PCSK9 trials, Fourier and Odyssey. PCSK9 inhibitors are basically the only drugs that are on the market that, in addition to lowering apolipoprotein B dramatically, do lower lipoprotein little a concentrations in the 25 to 30% range. And they looked at the Fourier and the Odyssey trial when they gave those people, obviously one got alirocumab and the other trial evolocumab, the two PCSK9 monoclonal antibodies that we use here. And they did notice that even once their LDL-C was corrected, if you also lowered LP little a, there was additional lessening of residual risk, additional event reduction. And it seemed to optimize when you got the LDL cholesterol down to around 30. So for some reason, maybe you have a genetic LDL cholesterol of 10. Would high LP little a not matter? I mean, that would be a guess at this time. And I don't know that anybody has done a genetic study to look at that. But using what the PCSK9 inhibitors reducing it, you got to really reduce it a lot. And most people have elevated LDL cholesterol, ApoB, who are taking the standard lipid modulating drugs, statins or ezetimibe, never reduce their LDL cholesterol below 50. Some of them do, their ApoB below 60 or 50. So LP little, and those drugs would not be doing anything to LP little a, even though you would say, hey, you've reached the LDL-C goal under 70 of the guidelines. LP little a is still causing residual risk. And we actually have data from the statin trials that show that.
And so that residual risk, just to make sure I'm hearing that correctly. So you can enroll subjects in a study who have pre-existing cardiovascular disease. You can put them on lipid-lowering drugs, get them to goal, so get their ApoB down to 30 milligrams per deciliter, so LDL's right down. But there's still going to be some people that have cardiovascular events. So are we saying here that it might be that those events that are occurring despite very low ApoB could be driven by elevations in LP little a and the effect that that is having on pre-existing plaque?
Yeah, or it's LP little a is part of initiating plaque also, not making existing plaque worse, which it does, but it's part of the initial atherogenesis cascade also because of what it's bringing into the artery wall. It basically starts the inflammatory process a lot sooner. But there is another little part of this story that shows you how much perhaps you have to reduce lipoprotein little a, and it's from the Mendelian studies, where they certainly have shown it's causal. High LP little a is causal of both atherosclerotic disease and the other side, the calcific aortic stenosis. But we're talking about atherosclerotic disease. And from the Mendelian data, you can deduce, well, how much do you really have to lower LP little a before all of a sudden the atherosclerotic signal disappears in the Mendelian study? And the first one that was published, and was a big evaluation, shows you probably have to reduce LP little a concentrations by 100 nanomoles per liter. So that's, 100 milligrams per deciliter. So that's a big drop. And even PCSK9 inhibitors, which I just told you, did seem to reduce risk a bit, not totally. They're only reducing it by 20, 30%. You're never going to drop an LP little a by that magnitude with a PCSK9 inhibitor. That will be the realm of the new drugs that are coming that we alluded to that interfere with the construction of LP little a, either genetically or with the marriage of apo little a to ApoB within the liver. So you're pretty much always going to have to worry about LP little a. Most doctors who are even treating lipid disorders are not lowering LDL cholesterol to 30 or ApoB to 30. Some in the know or on the avant-garde are, but most are not. They're saying, hey, if I can get your LDL cholesterol below 70, I'm doing a good job. One reason they say that is because to drive it any further, you have to adding a third and a fourth drug to drop it so much with the current state, and that gets to be problematic for a lot of reasons. So there is residual risk. The biggest trial that sort of showed that was the Jupiter. I think the Heart Protection also showed it. Is in the Jupiter trial, which is a lot of people, and they were tested with rosuvastatin, which is a very good drug at lowering LDL cholesterol. But they had a number of participants who had high LP little a. Most people know statins do not decrease LP little a. So if you're going to give rosuvastatin to somebody with high LP little a, you will reduce their LDL cholesterol, their ApoB of the non-apo little a LDL particles, but you won't reduce LP little a mass or particle number. But in the people with high LP little a, rosuvastatin did lessen the occurrence of MACE. Now, they didn't lessen it as much as they did as rosuvastatin to the people who didn't have high LP little a, which just goes to show you lowering ApoB by itself or LDL cholesterol helps a lot, but there will be residual risk if LP little a remains high. And so you can't lower it with a statin. So statins are a key part of getting LDL cholesterol and ApoB of the regular LDLs to goal, but you're not going to solve any LP little a mediated pathology with a statin. Ezetimibe likewise has no effect on LP little a, has a nice effect on ApoB and LDL cholesterol, but you're going to have residual risk with that. So that's why ultimately we're going to need Apo little a lowering therapies. And we will talk more about the PCSK9 whenever as to how that lowers LP little a.
Yeah, your point there about statins reducing risk of MACE in patients with elevated LP little a, I think that will be comforting to some people listening, Tom. I've seen people on social media point to various pieces of evidence suggesting that statins either have no effect on LP little a or may even increase LP little a little bit. And there's this fear or concern out there, I think rightly so, from someone who is hearing that but is not sort of in touch with the data, that thinks, hey, hang on, I'm hearing LP little a is the bad guy, and I'm taking a drug that could be even increasing it a little bit. But the point that you're making is that overall, despite its effect on LP little a, what you're seeing is a net benefit.
Yes, and this is a big problem out there because it's mostly the statin deniers, the statin haters who tweet all day long about, oh my God, never take a statin if you have high LP, even though every guideline is telling you that if you need a drug to reduce vascular risk in a patient with high LP little a, apart from lifestyle, whatever else you're doing, a statin is your first line drug because it's an ApoB lowering drug. Now, and this is here's a great teaching point I have to make in this podcast. So remember, I told you the LDL family, if you have the gene that makes LP little a, consists of regular LDLs that don't have Apo little a attached, and of course it consists of LDLs that do have Apo little a attached. So take this to the bank. Even in people with extremely high LP little a particles, it is a minority LDL particle. What do I mean by that? So let's say a horrific LP little a concentration would be 200 to 300 nanomoles per liter. What is a normal if I counted the LDL particles that don't have Apo little a attached to it, what's a normal number? Around 1,200 nanomoles per liter. So even with an extreme LP little a of 300 nanomoles per liter, you got 4 to 5 times more regular LDLs. So if I give you a statin, which will dramatically get rid of your normal LDLs by 30, 40, 50%, depending which statin, which dose, or much higher if you add ezetimibe to it. So I get rid of all those regular LDLs, which are the primary cause of atherogenesis, but I increase your LP little a by 5, 10, 20%. It goes from 300 to 320 to 350 nanomoles per liter. So I've given you a trivial number increase in LP little a particles while at the same time dramatically getting rid of your normal LDL particles, which explains why statins, you'd rather they didn't raise LP little a by anything, but the inconsequential amount they raise it is nothing compared to the benefit of getting rid of your regular LDL particles. And this is such a crucial point to make. Very recently, we had a nice study that came out that, look, particle for particle, an LP little a particle is far more atherogenic than an LDL particle, except you have 3 to 4 to 5 to 6 times more LDL particles than you have LP little a particles. So you can't worry about increasing the bad guy a little bit while you're getting rid of the other really bad guy by a hell of a lot. And that comes down to that.
I'm imagining the difference here between walking down a dark alley and being confronted with one martial arts black belt versus walking down a dark alley and being confronted by 6 brown belts. The black belt is far more dangerous on an individual level than the brown belts, but I've got more chances of knocking him out or running away from him than I do with the 6 brown belts. At some point, it doesn't matter how dangerous the single fighter is, a collection of fighters will be harder to combat.
No, it's there's many cool analogies like that that you can do. And again, while we're on this topic, so we sort of stay a little bit focal. How do statins raise LP little a? Now they don't do it in everybody. It's a minority of people they do, but they could. And this is most people say, hey, there's never a reason to repeat LP little a right now. But if you're going on a statin, should you repeat it? There are thought leaders who say yes, because you might get the real oddball who gets a 50% increase, but even that, it's still a minority particle. So if you're interested to see what the statin does, by all means, repeat your LP little a. But you have to repeat your ApoB too to see how much you're dropping that. And you would say, all right, I'll take that. So here's what happens. Apoprotein little a is made in the endoplasmic reticulum. There's a nice study that shows statins in some people, and no doubt it has to do whatever the hell their genome has, can increase the production of the low molecular weight, the small apoprotein little a, which of course is the isoform that can raise LP little a particle counts a little bit. So that may be the mechanism. But again, statins dramatically upregulate the LDL receptors, which is what pulls out all those brown belts you're talking about, the non-apo little a containing particles. The LDL receptors the statin don't pull out too many of those black belts, so they're still there, and maybe they're being produced in a little excess quantity, but you really haven't endangered yourself. If you started with a very high LP little a, you still got a very high LP little a. What will not happen to you if you have a normal LP little a concentration and you go on a statin because your ApoB is high, you will not push yourself into a high risk LP little a concentration. So it's just such a non-issue. People should read this textbook published 2 years ago. Peter Toth is the editor, but the Kastners are two world-class LP little a guys. One is probably Australia's biggest lipidologist, Karen Costner. And there are several chapters here devoted to this. That we're not even going to discuss statins and what they do. They go through all of that. It's just a non-worry.
And this understanding that there are 5, 6, perhaps more times as many LDL particles as there are LP little a, also, I think explains why you like to test LP little a, even if someone's ApoB is what you would say is optimal or normal, because it makes up such a small fraction of ApoB. What I'm hearing and understanding is that you could have relatively normal ApoB, but then run a test and LP little a is high.
Yeah, high in the atherosclerotic range or the aortic stenosis range, and yet you're not going to diagnose it by looking at LDL cholesterol or ApoB. So it makes so much sense, since it's so available and it's so cheap, that it should be a one-time test in your life. I did it years ago on myself. I know I never have to repeat it again because I'm not getting any gene transplants anytime soon. So it's comforting to know. Now, I do have atherosclerotic heart disease. I'd be worried a lot more about myself if I had concomitant LP little a on top of my ApoB. I've very successfully treated my ApoB, so I'm not worried at all now, but I would be worried if I still had a high LP little a that I really couldn't do much about. I might say, hey, I'd jump on a PCSK9 and I'll take that 25% and hope that matters, but that's another issue.
Yeah, that was going to be my question. You were talking about earlier the patient on statins, the oddball that might see a significant elevation in LP little a. Is that the current kind of clinical approach where you might see if that patient can maintain the ApoB level that you've achieved with a statin with a different combination of drugs, perhaps the PCSK9 inhibitors, so you're kind of optimizing best of both worlds there, ApoB and LP little a, until we have results from some of the trials that are underway?
Yes, and the the little bit of a bandwagon for the people who are jumping on, let's use a PCSK9 inhibitor in people with high LP little a, have looked at the Ferrier and Odyssey studies where PCSK9 induced lowering of LP little a. Didn't eliminate atherosclerotic disease, but it did improve residual risk beyond but LDL-C lowering with statin and PCSK9 is. So therefore, if you had high LP little a, and of course, you're treating your regular ApoB, your LDL cholesterol, with a statin or statin ezetimibe, bempedoic acid, whatever you're using. Why wouldn't you add a PCSK9 inhibitor to also get a concomitant lowering of the, and there's one reason why you wouldn't do it, because it doesn't have an FDA indication to do that. So you'd have to use the drug off label, which means no third-party payer is going to reimburse a patient for, in the United States, a $6,000 a year drug. So if you can afford $6,000 a year, and you've got an astute lipidologist who's practicing what my buddy Peter Attia would call medicine 3.0, you would encourage the use of a PCSK9 and get that, because you know, the Mendelian studies would tell you that type of drop in LP little a shouldn't work. But the data from pre-specified endpoints, albeit them secondary, in the Ferrier and Odyssey trial shows it probably does work a little bit. So why wouldn't you use it if you could afford it? You're not, the only way you could get a third-party payer to do it is if your statin hasn't gotten your LDL-C to goal. They would allow you to add a PCSK9 inhibitor to get your LDL-C to the guideline prescribed goals, but they wouldn't say, oh, you're also going to help your LP little a. They could care less.
So what's the mechanism here with PCSK9 inhibitors? My understanding with ApoB is that the PCSK9 inhibitor stops the kind of breakdown or degradation of the LDL receptor. So you get more of these LDL receptors at the liver. And with that, you can kind of clear more ApoB containing lipoproteins. So ApoB comes down. How is a PCSK9 inhibitor influencing LP little a levels?
Your description is 100% correct. As an aside, statins and ezetimibe and bempedoic acid, by depleting the cholesterol pool in the liver through synthesis or absorption inhibition, the liver expresses more LDL receptors. A PCSK9 allows those LDL receptors to recycle for a longer period of time than they ordinarily would. In other words, they don't get catabolized as quickly as they would. And the more times you can recycle LDL receptors, the more ApoB clearance from plasma. But I sort of explained before, those LDL receptors are phenomenal at clearing regular ApoB particles. But if Apo little a is on an LDL particle, the LDL receptor has a specific domain that is looking for a specific domain on ApoB. And if those two domains line up, they attach and you clear the particle. Apoprotein little a sort of camouflages the ApoB binding domain on the ApoB peptide. So all of a sudden, this LP little a cruises by an LDL receptor, but the LDL receptor doesn't recognize it as an LDL particle, so it doesn't get cleared, and its plasma residence time is longer. Now, if you express enough LDL receptors, you probably do get some clearance. There's an atorvastatin at a very big dosage use combined with a PCSK9 inhibitor that shows the statin is additive to the PCSK9. But you have to really use a big high-dose statin in that. For the most part, if you use the doses of statins that are being used, you're not going to clear LP little a particles. But we do know PCSK9 lowers it by 25 to 30%. And here's the cool part. So back to my little ribosome endoplasmic reticulum, which is making apoprotein little a, which is going to break free. And it sort of has to swim over and find a primordial ApoB particle that has the right contour of the ApoB that the Apo little a can attach. By the way, remember I told you there are 10 segments of Kringle 4 type 2? Well, Kringle 7 and 8 have a very weak lysine binding group in there, and that is the first attachment to the ApoB. those two kringles have a weak attachment to ApoB. And once that attachment occurs, then there's kringle 9 that has a much stronger lysine binding domain that binds to a sulfur group, cysteine group on the ApoB, and you have what's called the disulfide bond linkage, and that's how you create the particle. But if we could prevent the apo from getting anywhere near the primordial LDL particle, that binding couldn't occur. So there's two things you could do. You could stop if you had a drug that inhibits the synthesis of apoprotein a, that would, of course, screw it up. Or is there a protein that grabs apoprotein a once it's produced and sort of helps it swim over? It's called the chaperone protein, where the apo a could then bind to the apoB. So here's the evidence for PCSK9 inhibited is it somehow takes ApoA, which is produced, and doesn't allow it to bind to the LDL particle. So I use the chaperone protein analogy. So if PCSK9 is chaperoning ApoA to the LDL, if you inhibit PCSK9, there's no chaperone protein anymore, and your apo is not going to find as many LDL particles to bind to. Of course, it could maybe shut down production of apoprotein a at the ribosomes. I don't know that they have a lot of data showing that, but either or, this is still early in its investigation as to the mechanism of action. But you will reduce production of Lp(a), enough so that you get a 20-30% reduction in Lp(a) particle concentration. So you're not really clearing them, you're underproducing them. Maybe if you add a really high dose statin to the PCSK9, you will enhance a little bit of clearance, and you'll see even a little better drop in Lp(a). One other aside, there is a drug in development. We've known for a long time, CETP drugs, they're on their 7th one now, and several have failed to reduce MACE. The next level, not the one that's being produced now, but anacetrapib did reduce MACE by about 5%. It did drop ApoB a little bit, unlike all the other predecessor CETP inhibitors. But all of the CETP inhibitors reduce Lp(a). So there's always a hope that, wow, they might have an accessory use. If you could ever use them for what you're using it for to reduce MACE, you might drop Lp(a), and who knows, would that give you even better event reduction? The anacetrapib was never brought to market because it somehow mobilizes in adipose tissue and stays there for years, so the company didn't want to play that game, give you this drug, and 8 years from now something shows up bad. But the new one in development, obicetrapib, drops ApoB significantly by 15 to 20%, way more than anacetrapib, but it can drop Lp(a) by 50 to 60%. So the hope is that drug is going to work because it really lowers ApoB as much as ezetimibe. Any drug that drops ApoB that much reduces MACE, same amount as bempedoic acid would do. And God, what if we could reduce MACE because it lowers ApoB, but that degree of lowering Lp(a) holds potential. So stay tuned. And it is now believed that obicetrapib and the other CETP inhibitor inhibit synthesis of apoprotein a. So there is perhaps a true synthesis. Much more work needs to be done. That's very preliminary data suggesting that's its mechanism of action. So now, but I will have to mention this. There's a drug going into, I believe it's in phase 2 right now, called muvalalapin, Muvalapin. Maybe my spelling is wrong. But it also prevents the binding of apoprotein a to the primordial LDL particle, so therefore will dramatically reduce Lp(a) concentration. Not as much as the ones that are the ones that act on the genes, which will basically shut down apoprotein a production, but they're talking about a 60% reduction in Lp(a), and their hope is in a primary prevention setting, that would be a spectacular drug. Not in a secondary prevention setting where you really have to eliminate it. And the same would be true with obicetrapib. Would it be good for primary prevention of Lp(a) patients? Now look, both of those would have to do serious outcome studies to prove that to the FDA. So we're talking years before we're going to see those drugs used for that, unless somebody uses OB off label, because that is probably going to be on the market sooner rather than later. So we're learning a lot.
Just to kind of bring everyone up to speed with the drug interventions that you're talking to. So other than the kind of trial, I think you said Odyssey, that looked at the PCSK9 inhibitors and saw some benefit for residual risk, and that's in a trial where they're looking at ApoB lowering drugs, which happen to lower Lp(a) as well. By a little bit, 20-25%.
And they're also serious. They have serious atherosclerosis, those people. They're not, that's not a primary prevention type stuff.
So that's a secondary prevention type study. Other than that, the science that we have to date on drugs that target apoprotein a synthesis and looking at lowering Lp(a), there's evidence showing magnitude of reduction. So in the ballpark of 50, 60, 70% or more, depending on what that medicine is. My understanding is, though, the next step now is to see, okay, in whatever clinical population we're talking about, if you use that medicine to get Lp(a) down by whatever percentage was achieved in the other studies, what does that actually mean for the individual in terms of heart attacks, strokes, etc.?
Yeah, and so that ultimately would require a mega outcome trial, which costs billions of dollars. So those companies may not be willing to spend that type of money to prove in a primary, but they might be able to do some imaging study, show, hey, you have clean arteries on a CTA or a coronary calcium is 0, and it stays that way over a few years on this drug, as opposed to the people who didn't take the drug, maybe show some plaque development. Maybe that would be an easier step, way more affordable step to at least say, I have some efficacy here. Whether the FDA would buy that or not, I don't know. But I just don't see those, and those are smaller drug companies, unless some big pharma buys them to invest the billions of dollars in a primary prevention outcome trial. We may never see that with Lp(a).
But they are being done like in Horizon in a secondary prevention setting.
Yes. The anti-sense drugs, the siRNA drugs, which will basically eliminate apo(a) production, they are all looking at super high-risk people. And this would be the problem. We're all, fingers crossed, believe as long as there's no adverse signal from those drugs, they're going to reduce events, MACE. But nobody foresees the FDA giving them primary prevention indications. They're going to say, hey, secondary prevention indication. And without an indication, third-party payers are not going to pay for it. And my guess is if we think PCSK9 inhibitors were expensive when they came on the market, wait till you see what these niche drugs are going to cost. And without third-party paying, it's going to be hard for the most people to even use it.
That gap there and this kind of understanding that there's probably not going to be a big primary prevention trial, I think that's what kind of opens the door to this exploration that you see online from people talking about diet modification or niacin or fish oil, things that they can do within their lifestyle that could influence their Lp(a) level. And I'm talking here to the person who would be low risk of cardiovascular disease. They have no history of high cholesterol or high blood pressure, no family history. They exercise regularly, they eat well, but they go and measure their Lp(a) and it's 150 nanomoles per liter. That person there is wondering, is this just something that I deal with? That's my genetic fate? Or in the absence of clinical studies looking at my population, are there things that I can do to modulate my risk?
Sure. And whatever you do, you're using anecdotal data or very weak data to suggest, hey, lowering Lp(a) by even a small magnitude is beneficial. you're taking the ApoB belief that lower is better would apply to LP little a, but the real question is how much lower do you really need? So niacin, the guidelines strongly advise not to use niacin. You have to use niacin in pharmacological doses to impact LP little a. You can't use a one-a-day vitamin with that dose of niacin to get benefit. Niacin has failed to reduce MACE in 3 major primary or secondary prevention trials, and there was significant toxicity to the drug. So you're using a toxic drug to drop LP little a, and there was nobody's ever taken a trial of LP little a patients and randomized them to niacin or placebo to prove that, it would overcome even the toxicity of niacin. And the biggest toxicity is insulin resistance, type 2 diabetes, the appearance of acanthosis nigricans in the skin, atrial fibrillation, ulcers, the magnitude of side effects that we now know, hemolytic disorders with niacin. So it's been removed from the market in Europe, so you can't even use it there, at least at those type of doses if you wanted to. So niacin, nobody should do. Fish oils, I mean, people have been talking about that for years. I believe most people should be taking, I would measure your omega-3 levels using a validated assay. And if you're low, all of us should be taking omega-3 fatty acids. And if you have high LP little a, and it'll help you, great. If you have, for some reason, maybe you're Norwegian or you're eating so much darn fish that you have perfect omega-3 levels in the blood, if there's benefit with LP little a, you've probably achieved it already. So I would use a blood test to decide. And whether it's helping LP little a or not, I think anybody with low omega-3 indices should take omega-3 fatty acids. A little caveat there I was thinking about the last few days. The bad news with LP little a, I mentioned atherosclerotic coronary disease, and we mentioned calcific aortic stenosis. But now let's go down the list. Major risk factor for peripheral arterial disease. A major, not quite as high, but for ischemic stroke, LP little a. So, there's a lot of bad stuff with LP little a that you should. But lowest on the list is high LP little a is associated with atrial fibrillation in some people. Now, is that because of coronary disease, or does LP little a somehow affect the conduction system? And remember, a minority of people who use fish oils, one of the consequences is atrial fibrillation. So I don't know. It's like anything else. I think I wouldn't worry about atrial fib, but I would inform a patient to know if atrial fib is happening. This is what you will experience: a fluttering in your chest. Maybe you're weak, you're tired, you're dizzy. And if you feel your pulse, all of a sudden you can't feel it anymore, or it's very irregular. So I think we can educate people for that type of side effect. So I think people are going to try it. If they go on their favorite diet and they lower it by a little bit, fine. I don't care if they stay on that diet, but will that work? I don't know.
I think that speculation around fish oil with regards to LP little a comes from the kind of anticoagulant, anti-inflammatory properties that fish oil may have. And in a similar vein, this is where people also bring up aspirin. How would you feel about someone with elevated LP little a taking aspirin?
And my thoughts on that changed this year. Now, when I was in practice for years, if you had LP little a, the whole etiology, it's a prothrombotic protein. So, hey, take aspirin. Why not? If there's some excess coagulation going on, maybe aspirin can help it. And we even now know that they could activate platelets. We didn't know that back then, LP little a. So aspirin always made a lot of sense. There was a study, first the women's health study, that came about 10 years ago in postmenopausal women, that if they had a certain SNP associated with LP little a, they had dramatic reductions in MACE by using aspirin. But if you didn't have that SNP, aspirin did nothing to preventing events in women. So that was a hypothesis. Now, a couple of years ago, out of the ASPRI study, which was looking at aspirin in elderly people, they saw the same damn thing, and they investigated this particular SNP. on the premise that, hey, if it worked for postmenopausal women with this SNP, maybe it'll work for elderly people with it or so. And indeed it did. So there is evidence that if you have this LP little a aspirin SNP, aspirin is probably well indicated for you. Because remember the old theory, if you put aspirin in the drinking water, there'll be X number of cerebral hemorrhages or other bleeding issues that can occur. So you got to be careful with it by, hey, everybody should take aspirin. There's secondary prevention of ASH, everybody's given aspirin. But in primary prevention, there was always that worry. Now, a few months ago, just was published the MESA study. We all know the multi-ethnic study of atherosclerosis is a whole bunch of people of different ethnicities where they're looking at all sorts of things, especially cardiovascular risk factors. And lo and behold, people with an LP little a above 50 milligrams per deciliter had a dramatic 30 to 40% reduction by aspirin use. So once I saw that, to me, primary prevention, you're going on aspirin, unless there's a reason not to use aspirin, of course, or if you suddenly start the aspirin and it bothers your stomach or you start bruising or something. But that MESA study is pretty impressive. If you don't have the reference for that, so I'm going to got to give it to you. The show notes and everything. And you'll see the Kaplan-Meier curves. They're very impressive.
And it's not that aspirin lowers LP little a, it's that it may be kind of offsetting some of the pro-thrombotic properties.
Yeah, there is a little bit of theory that it might lower LP little a little bit, but, more of the theory is on the platelets. And now especially the Marlis Kaczynski and Michael Boffish showed that LP little a can induce platelet adhesion. So sort of makes sense. And there's not a lot of downside to aspirin.
Are there any drug trials, Tom, looking at anti-inflammatory medicines, given LP little a's kind of pro-inflammatory properties? Is there a hypothesis or speculation that reducing inflammation in the body may be beneficial for someone with elevated LP little a?
Well, there's sure a lot of talk about it because now we're going to get into the other reason and the primary reason why LP little a is feared today. Those procoagulant effects have moved to the back seat. Probably a contributor. But the major pathology wreaked by LP little a particles is it's carrying something. And remember, there's Kringle's 4 and Kringle's 5. This is easy. We're now going to talk about Kringle 5. There's no subunits to Kringle 5 that you have to confuse yourself with. But there is an incredible binding site, a lysine binding site on Kringle 5, which has tremendous affinity to bind to something called oxidized phospholipids. Oxidized phospholipids are one of the major drivers of inflammation in atherosclerotic disease and likely in other diseases also. So lipids can be oxidized. The simplest way, oxidize is you're turning something on fire. That's, a 4-alarm fire is an oxidative process where wood is being oxidized. It's burning. So if you can take lipid moieties that have been oxidized, they're incredibly destructive to whatever tissue they might wind up in or bind to. So what is on the surface of LDL particles? Phospholipids. So if those phospholipids are being oxidized, that makes an LDL particle way more dangerous than if it wasn't carrying oxidized phospholipids. Now, everybody has known for years there's a blood test called OxLDL, oxidized LDL, a totally useless blood test that is not measuring oxidized phospholipids. So don't please start ordering that blood test and thinking it's telling you anything about either atherosclerotic risk beyond what ApoB tells you, and certainly LP little a mediated risk. But So it's now theorized that lipoprotein little a is sort of like a garbage truck that drives around and it binds with high avidity to dangerous oxidized phospholipids and may be a way of helping disposing of these very dangerous lipid moieties. So, wow. So, therefore, if you're removing LP little a particles, if that particle is carrying a lot of oxidized phospholipids, you're probably doing good to get rid of those. You get rid of them in the liver can get rid of them, or if, even white blood cells or the reticular endothelial system may be a way to help get rid of those particles. Who knows? But so these
Tom,
oxidized
can I interrupt
phospholipids.
you?
Yes.
Can I interrupt you there just for 1 second? That's really interesting. So you're saying that LP little a may chaperone these oxidized phospholipids back to the liver, helping get them out of circulation, which would reduce the threat that the oxidized phospholipids pose. Now, if I'm thinking about drugs and reducing someone's risk here, it would seem to me that if you're reducing the production of apoprotein little a, then you may end up with less of these chaperones to bring oxidized phospholipids back to the liver, which would be different to if you were helping the liver just clear more LP little a's.
Yeah, and that's why you need outcome data. And even think of these drugs that are going to eliminate lipoprotein little a. What if you're removing a scavenger hunter for oxidized lipids in these people? That you may make LP little a concentrations disappear, but there would be no event reduction. So, I mean, these are all hypotheses on the table. So who knows? So even the LP, you're lowering it a little bit with a PCSK9 inhibitor. You think you're doing good, and you might be reducing MACE, but are you injuring other tissues? Remember, these LP little a particles, circulating monocytes can internalize them, and then they become pro-inflammatory white blood cells. So the story needs to be told on what modulating them oxidized phospholipids mean. There's kind of interesting data that statins do not lower oxidized phospholipids, and is that some of the residual risk of statins lowering ApoB, but they're not lowering oxidized phospholipids, so there's still some bad stuff going on. We're just in our infancy. This is a recently discovered thing. The assays that measure it are debatable at best. There's only one lab in the country now that will, at least in the United States, that will offer you an oxidized phospholipid test. But I think it's a very interesting marker. Just one last thing, I'll let you speak. If I had two people with very high LP little a, and I measured oxidized phospholipids on ApoB, and it's high in patient A, but not high in patient B, the patient with the high oxidized phospholipids is probably at much higher risk than the patient with just isolated LP little a elevation. There is data that shows that now, but it's a very interesting thing. And it just binds to that one little kringle there. But maybe that's the function of LP little a.
You just answered my question there. But just quickly, what is that lab? What's that lab called if someone wants to order an oxidized phospholipid test?
And the assay was developed by one of the world experts on LP little a, Sam Samikas, out in UCSF or USCD, San Diego. He's done immense studies on this, and he developed the what he thinks is the best assay for this now. And the one lab that bought it, and it's a proprietary assay, so obviously it costs the lab money, is Boston Heart Lab, which is obviously in Boston. If you Google them, you'll see them. And on their search menu, just type in OXPL-ApoB. An interesting thing there. It sounds like all the oxidized phospholipids are on ApoB. They're not. They're on the ApoB particle. And the oxidized phospholipids would be on the surface of the LDL moiety. There'd be a few of them stuck on the ApoB moiety, but most of them are stuck on the kringles of LP little a. So if I took out the family of LDL particles If I had the big or normal size LDL particles, you would find almost no phospholipids on them. Now, if I went to the small LDL particles, people call them small dense. That's a redundant. I either call them small or dense. They have a much more higher magnitude to bind to oxidized phospholipids, which, by the way, if small LDLs are more atherogenic than big, that's probably one of the reasons they're packing oxidized phospholipids. But the particle that carries the vast majority of oxidized phospholipids are Lp(a) particles. So if we measured in a patient oxidized phospholipids on ApoB and it came back high, and you haven't already measured Lp(a), you better on your next blood draw do it, because that's going to explain most of the very high levels of oxidized phospholipids on ApoB. Right now, for the docs who are screening with Lp(a), if it comes back high and you're not sure what does it mean, please do the oxidized phospholipids. It's a little bit more information right now, although we still have a lot more to learn.
I have two questions for you here, Tom. The first one is, what causes the oxidation of the phospholipids?
And the second one is, go ahead.
And the second one is, and I'm sure studies have looked at this, if you adjust for oxidized phospholipids, does Lp(a) still predict risk?
I think the answer to the second question is yes, but it might predict more risk if it was carrying oxidized phospholipids. So yes, Lp(a) is, you should always assume, is dangerous, but perhaps more dangerous in that environment. But and how does a phospholipid get oxidized? Well, a phospholipid, we never really discussed what it is. It's a glycerol lipid, which means it starts off as a 3-carbon sugar called glycerol. And there are 3 carbons, so 3 things have to be attached to it. And the carbon 1, it's called the stereospecific number 1. Carbon 1 binds to a phosphorus moiety. It might be phosphatidic acid, or it might be other moieties that contain a phosphorus moiety. So that's the first thing on a phospholipid. But the next 2 legs on carbon 2 and carbon 3 are just fatty acids. And often on carbon 2 is arachidonic acid, a very pro-inflammatory fatty acid. So if you have an enzyme that starts cleaving or makes the glycerol lipid undergo lipolysis, and you start losing fatty acids, you're then going to be left with a glycerol molecule that has the phosphorus moiety attached and 1 fatty acid. So it's lost a fatty acid. Phospholipid with 2 fatty acids is called diradyl, R-A-D-Y-L. But if you have just 1 fatty acid, it's called a lyso, L-Y-Z-O phospholipid. But you've cleaved something off of that, and it's the phospholipase A2. It's a specific lipase that cleaves the fatty acid on the second carbon that in most cases frees arachidonic acid, a pro-inflammatory fatty acid. But even other fatty acids that are cleaved, they often carry double bonds. They're very amenable to oxidation. So it's the cleaved fatty acid that gets oxidized. But now the lysophospholipid that is left is lysophosphaditylcholine. That's a very atherogenic lysophospholipid. So the enzyme that takes away the 1 fatty acid, in essence, creates a very atherogenic fatty acid and a very atherogenic lysophospholipid. So those are the things that shoot into the tissues and do the damage. So what is the enzyme that does that? It's lipoprotein phospholipase A2, LP-PLA2. Many people have heard of that because they're ordering it as a blood test to ascertain inflammatory risk. So it's an enzyme that is carried with high intensity on small LDL particles, and it's a major part of the Lp(a) particle. So if you're carrying an enzyme that decides to start cleaving the phospholipids on that particle, Wow, you got a messy substrates that are created. So this is why perhaps measuring LPPLA2 is known to, most people will go with C-reactive protein, but LPPLA2, if it was elevated, I think it's a signal to you, boy, if you haven't checked it, you better do an LP little a on the next blood test. Very interesting to show you how complicated this is. They notice about LPPLA2 being generating proatherogenic lipid moieties, and it came to reason that if we could just inhibit this enzyme and stop it from cleaving the phospholipids, you would have a cardioprotective drug. And they developed two phospholipase inhibitors that pretty much shut down LPPLA2 activity, and they did randomized blinded large outcome trials, which were null. So interesting, you can use LPPLA2 as a risk factor, but never as a goal of therapy because inhibiting it didn't matter. Now, they didn't measure oxidized phospholipids in that study to see what happens to oxidized phospholipids when you take away that enzyme activity. I'm imagining there are other phospholipases that can generate oxidized phospholipids also. So it's just a very interesting story there. So, but to take home, so many people are measuring the plaques test, LPPLA2, just because they think it's another CRP. They think it's atherogenic specific. It's not, but it is a pro-inflammatory enzyme. But if it's high, please, if you haven't already measured LP little a, measure it.
And what influences that enzyme level? Like what part of someone's lifestyle? For example, you often hear people saying that oxidized LDL is really the problem. We've spoken about this before, but there's this school of thought out there that it's not LDL that's the problem, it's oxidized LDL, or if we want to be more specific, oxidized phospholipids. And people will take that further to say, this is why you should consume saturated fats, which are more stable, and not consume higher amounts of unsaturated fats or vegetable oils, for example. I'm not sure if you have any views on that from a dietary point of view.
No, but I understand where you're going. The more oxidizable fatty acids have double bonds, whereas the saturated fat is less prone. Also, remember the oxidation occurs in the artery wall. LPPLA2 is not. It starts its enzymatic action within the arterial wall. So where we're not measuring what's going on, it's not. This oxidation is not occurring in the plasma. So just keep that in mind. So if you would say, hey, I'm going to send saturated fat into the artery wall, it don't matter because it can't be oxidized. There would be other fatty acids in there that could be. But by consuming the saturated fat, you're down-regulating your LDL receptors and driving ApoB through the roof, which is encouraging those LDLs to crash the artery wall where oxidative processes do occur. Regardless, even if you're some of your fatty acids on the phospholipids are saturated fat. The SN2 position pretty much binds unsaturated fatty acids. The saturated fat would be on the SN3 position. So you're not really reducing inflammation, but
earlier you mentioned that LP little a is driving risk through kind of two different pathways, pathologies, one being atherosclerosis, which we've spent a lot of time here on with the pro-coagulant, pro-thrombotic, pro-inflammatory properties. You also mentioned calcification of the aortic valve. So briefly, before we kind of wind up here, how does LP little a affect the aortic valve, and why is that important for us to consider?
Well, it's been known for a long time that even high ApoB is associated with aortic valve. Remember when ezetimibe first came on the market, they knew it's a weak ApoB inhibitor, but if we combine it with statins, it'll be a real strong ApoB inhibitor. And they had tied in very high LDL cholesterol. And nobody was using the term ApoB back then, but those in the know knew it was ApoB. So they did the first outcome trial with ezetimibe was the SIEGE trial, where they enrolled people with, unfortunately, end-stage aortic stenosis. And they said, but we're going to lower ApoB real and LDL cholesterol a lot, and therefore they will have less complications of the aortic valve. In that study, it did nothing to aortic valve disease, mostly because the valve was so damn damaged already, which maybe if you had done the trial when aortic stenosis was in its earlier stages, it would have worked. But in that trial, it did reduce ischemic events, the secondary endpoint, which was the first data that statins plus ezetimibe reduced MACE. But it did nothing to the aortic valve. But it was certainly known epidemiologically that high ApoB, high LDL cholesterol was associated with aortic stenosis. But then also came the Mendelian study, and Benoit Arsenault up in Quebec proved that, boy, it's causal for aortic stenosis as well as atherosclerotic heart disease. And a lot of studies have been done. So Lp(a) also can be pulled into the aortic valve, probably by the same damn receptors that pull it into the artery wall. And there are several, by the way. I didn't go into naming the 4 or 5 receptors because that's getting too deep into the dive. But it gains entry into the interstitium of the aortic valve, which is a lot of connective tissue, of course. And not only is it incredibly pro-inflammatory, so it's not good to make any tissue inflammatory, including the valves that open and close your aortic valve, but it has osteogenic potential in the aortic valve tissue, more so than it does in the arterial wall. So hence you're building bone in the damn aortic valve because of osteogenic proteins that are formed by its ability to defect whatever part of the genome regulates those proteins that are involved with osteogenesis. So obviously throwing calcium into valves that are supposed to be very mobile and very flexible, you're going to have valvular contraction irregularities and over time. So this is, by the way, if you understand this, any new patient who's younger comes in, most people don't know what relatives have had aortic valve disease, but if by some reason they mention it, you better be checking Lp(a) in that patient. But aside, everybody ought to have a once-in-a-lifetime Lp(a) test, and if it's high, I think at a certain age, you start doing echocardiograms, just like you would, for the vascular side, you just start attacking ApoB. You're not in 20-year-olds starting to do imaging studies to see, do they have plaque? But I think aortic valve, the knowledge is now you're probably going to need an aortic valve replacement at a certain point, and probably sooner rather than later. Once certain valvular pressures across the valve change, there is a ripe time to get in there and replace that valve. Because if you wait, then you start destroying the left ventricle and you're left with a bag by the time you replace the aortic valve, and a lot of heart failure and other complications. So using the Doppler echoes that they do nowadays, you really get a handle on how good is the aortic valve working or not. So I think you get a baseline echo, and depending on what it shows, periodic echoes. I personally, in the practice I consult with, if we see somebody with high Lp(a), we start doing the echo periodically. Remember, that's an ultrasound. There's no radiation with echocardiography, so it's a safe test. It's really a cheap test also. And you do it periodically. And if you start to see, the report starts coming back where you see things, then you would punt to if either a cardiologist or a cardiologist well experienced with aortic valve pathology. And remember, aortic valve replacement nowadays is sometimes even just done through the skin. You don't crack your sternum anymore to replace the aortic valve. In advanced cases, they can, but it's a much more trivial. You can go home the next day if that's what's done to you. So, but anyway, you watch the aortic valve.
So if someone considers themselves low risk of cardiovascular disease, Tom, let's say they're aged in their 30s and they get their Lp(a) tested, comes back at 150 nanomoles per liter, are you wanting that person to go and see a cardiologist at that point?
Yes and no. It depends. I think you have to get the echocardiogram if you're comfortable with looking at echocardiogram results yourself and know what the various parameters mean. You will know when they go south, and the reporter's probably going to say there's some deterioration, even if you don't know how to look at the echoes yourself. But yeah, if you're unschooled in echoes, I think at a certain point you should refer to a cardiologist. But uh, I'm going to get into the dim statistics now. You would faint if you knew how many cardiologists have no idea what LP little a is. They don't measure it in their practices. So if you're going to refer that, you better refer to a cardiologist you happen to know, knows and understands LP little a related pathology. Because if not, you and it's malpractice, you will have cardiologists. What the hell are they sending you here for? Get out of here. There's no problem. I don't even measure LP little a against guidelines, but so that is out there. You have to know what you're doing. But I think you could just keep doing echoes. It's going to tell you, hey, there's some deterioration in the aortic valve function here.
Tom, again, this has been a real treat to have you back on. Let me just summarize a few of the things that I've kind of learned today, and then you can build on or help us close this out. So LP little a is a kind of subtype of low-density lipoprotein that has an extra protein on it. And because of this, it takes on some different properties. It is prothrombotic, procoagulant, it can be pro-inflammatory, pro-atherogenic, pro-osteogenic, and all of these things can lead to a heightened risk of atherosclerosis, so getting more plaque in the artery wall and making that plaque kind of more vulnerable to causing an issue, and then also to dysfunction of the aortic valve. And all of us can go out and measure LP little a, which is something that you think people should do at least once in a lifetime. It's primarily almost entirely driven by genetics, so there's no need to be going out every month, every quarter, all the time ordering this. It's not fluctuating as much as something like LDL cholesterol or ApoB might, based on dietary changes. When you order it, there are different ways, there are different units of measurement. So a lab could measure the mass, milligrams per deciliter, but the preferred measurement would be particle concentration, which is nanomoles per liter. Ideally, if it's mass that's ordered, a low risk level would be under 30 milligrams per deciliter. If it's particle concentration, it would be south of 50 nanomoles per liter. When you're up into the territory above kind of 50 milligrams per deciliter or 100, 125 nanomoles per liter, and you're into that moderate to high risk category, then what you do with that is somewhat determined on your baseline risk of cardiovascular disease, is kind of what I've heard. So if you're someone who has no history of cardiovascular disease, then my understanding is that you would be looking at making sure your ApoB is optimized, and obviously making sure you're exercising, not smoking, all these other risk factors like your blood pressure's checked, all of those types of things. In the absence of evidence that's looking at primary prevention, drugs lowering LP little a and what effect that might have on your overall risk. If someone gets an LP little a blood result back, it's in high risk category, but they are a high risk cardiovascular disease patient with a history of cardiovascular disease that's taking lipid lowering drugs. In that scenario, there may be a conversation to be had with cardiologists to think about not only optimizing ApoB, but driving LP little a down a little bit with a PCSK9 inhibitor until some of the trials that are underway looking at much more dramatically lowering LP little a are published, and we have data on that and clinical indication for specific drugs that lower LP little a.
Yeah, your summary is pretty good. You could have just had a 20-minute podcast and read that and not had me on. You nailed it. So, two things you didn't mention. There are significant ethnic variations. I did mention the Africans. And the second most population is Southeast Asians. The Far East Asians, Japanese, Eastern China, they're no more different than Caucasians, but Indians, Pakistanis, it's a big problem in that ethnicity. And of course, the African American community. And where you said, hey, the mass above 50 is worrisome, there are people think above 30 milligrams per deciliter in African American is, you'd be at risk for it. So, there are some ethnic variabilities here in the ranges. And just like everything else, once pharma knows or strongly believes that lowering this is going to be beneficial, there are like 4 or 5 other products. Pelacarsen is the first one. They're well into their phase 3 trial, and hopefully that might print out in 2025. The next one is probably going to be 2026. The others are years beyond that. But it's like when we got the first statin, all of a sudden you ultimately saw 7 further statins, and the same within a blood pressure thing. So pharma is chasing LP little a. So the bean counters and decision makers there believe this is, and you know why? It's so ubiquitous in the world population. There are billions of people who have high LP little a. So there's a market out there. They're going to have to go and teach healthcare providers about this. They're going to have to jack up testing big time, but they believe they can do that. And with it being that prevalent out there, wow. And remember also, the CRISPR technique. So one day maybe it'll be a CRISPR therapy, a one-time infusion that shuts off that ApoA gene, and who knows? So the future is always bright in lipids, but I think with LP little a, it should be, provided there is no crazy downside to obliterating it. If there is some function it's performing that we don't recognize, we're going to find out. But listen, the Pelacarsen trial is they're pretty deep into the trial, and they're not seeing any adverse signal, or they would have stopped the trial. So I think we probably don't have to worry about lowering LP little a that much, whatever. So I'm trying to hang around long enough to see all this. I don't have LP little a, but it's been a topic of great interest to me for a long time, and worked in labs that were playing with assays to try and perfect its measurement. So it was a fun ride for several years for me.
Thank you very much, Tom. Once again, another masterclass. We're all so grateful for the time you dedicate to educating us. And for me personally, it's always such a pleasure, such a delight to be in your presence. So thank you once again.
Well, you're so very welcome. And it's a privilege to be invited by a podcaster of your status also. So because we have to get the message out. You try and you bring on the experts who try, and there should be good coming out of these.
There you have it, friends. I hope you enjoyed this episode. If you did and want to stay up to date with future episodes, be sure to hit that subscribe button on YouTube and follow on Apple or Spotify. Finally, thank you for showing up and the effort that you're making to take control of your health. I look forward to hanging out with you again in the next episode.